I'm Peter Donovan with the Soil Carbon Coalition, which is a small nonprofit or non-governmental organization in the United States. I've done a lot of monitoring of landscapes, soil health, and watershed function over the past dozen years, working with lots of different groups all over North America, ranchers, farmers, in places that are badly desertified, such as this one, and also places where people are doing a lot to improve the situation, improve soil health, improve watershed function, increase the amount of rain that infiltrates rather than runs off. And over the years, I've built a web app, atlasbiowork.com, open source, open data, and it's designed to be a support for participatory community science, which in turn is designed to support a large participatory learning process, a shared intelligence based on evidence, and that is also can be localized about soil health and watershed function and other issues, other resource concerns. And the next installment of the next development will be soilhealth.app, which is not live yet, but it will be an improvement and expansion of atlasbiowork.com. And what this does is record observations and results of experiments and display on maps. Data entry forms can combine text, numbers, photos with location for display on a map. Like Open Data Kit, it's easy to design and configure new data forms in a matter of minutes and put them up on the website ready for use. This web app can be used on mobile or desktop, any device with a browser such as a tablet, an iPad, an iPhone, a desktop computer, a laptop, with or without network. And data is easily exported via an API or an application programming interface. Let's look at Atlas BioWork here. Here's the home page, and it's a browser application, and fairly simple menu home page. It's easy to create an observation type using an Excel spreadsheet, for example, as a prototype, and eventually we'll be able to do drag and drop. But let's go ahead and add a new point site and data. Now, I'm using my cell phone network, so my cell phone is my location as determined by the browser is way far away from where I am. But let's just look up a location here, and I'll just point on the map to show you how easy it is to enter an observation. If I were standing in a field somewhere, this would be a lot easier. I would be located by my GPS on my phone. But I'll just point on the map there, and it gives us our latitude and longitude, and I'll click continue. And it has a menu of different data types that I can use, and from a simple photo to water infiltration to production per unit of input, evidence of soil health, some very simple and some fairly complex data forms here. You can combine both of them. I'll just use a comment. It's about the simplest form that I can do for this demonstration. And it asks me, are my observations accurate and well recorded, and could they be repeated? Because time series observations are very critical when you're talking about change over time in landscape function, in soil health and watershed function. So let's look at my comment here. I can see it, and it's located on the map. And the map I can also look at a street map and zoom in and out and move it around and so forth. See where I am. And you can zoom in quite far as well. Okay, so that's how to enter a piece of data. Let's look at some different types, the range of data that you can use these kinds of systems for. Here's one called Evidence of Soil Health. And I'll just pick one sort of at random here. And this asks 5 basic questions. It's not a numerical thing. What's the soil cover? There's very little evidence of any soil cover. There's total absence of plants, no residue, therefore there aren't any living roots. It's been recently tilled, zero diversity, no evidence of livestock. Unfortunately, very typical of large areas of California during the winter especially. Anyway, that's one example. And of course, this is all mapped. Everything is mapped. Let's look at soil carbon change, and there's lots of them. These are measured instances of soil carbon change. Let's look at this one here. And this shows a fairly substantial increase in soil carbon in the top 10 centimeters anyway, from 6 to almost 8%, and then 1.8 to almost over 3% in the 10 to 25 centimeter layer. And then the chart that's attached to this, it didn't display in the original thing, but now we can see it. It's highly numerical here. Okay, let's look at another type called photos, and this is a very simple type of observation, and it's just photographs. And here's an example. Photographs with a caption. Here it is, and the reason I took the photo was that this is a picture of a radish root encountering a strong compaction layer. And we can look at this a little bit more closely here. Again, fairly slow internet here. So the picture is taking a while to load, but here the radish root was working into the ground and encountered a strong barrier that it could not immediately get through. And that's probably an evidence of a compaction layer about 2 to 3 inches below the ground, below the soil surface here. And we can look at another example of a photo here that shows a much more technical type of observation. And anyway, showing you the range. Here's hydraulic pressure testing in a well, a 40-foot well. We look at this more closely, we can see that this enabled the detection of gravel, sand, and some clay, whereas the pressure increased to put water out through the well casing, mostly clay and that sort of thing. So this is a very detailed, highly technical thing. Okay, that's one quick way that you can look at that Atlas Biowork works here. And I want to show you one more thing. I can put .geojson at the end of a URL or a web address here, and it immediately spit out a machine readable version. So this data is not siloed, it's not locked into this website, it's very portable. And in the prototype of soilhealth.app, I am pulling data live from another website, in this case Atlas Biowork. And I'm looking at infiltration. This map is a very different kind of map. I can go to the street map, but I'm also looking at this length of green map, where the pixels are colored green depending on how many days in the year that photosynthesis, or normalized difference vegetation index, is above a threshold. So this is a very good soil health indicator in terms of the living roots, the cover, the diversity, and so forth. The forest lands are generally pretty green because we have a lot of conifers in northeast Oregon, and the grasslands are generally much shorter length of green because we have seasonal rainfall here. Let's look at an infiltration. Comes with a photograph. The data is not very well displayed here in terms of order or prettiness, but we do have it. And the first inch of water took 3 minutes, and then 29. The second inch took 29. A foot away, this took 11 minutes and 47. So there's a lot of variation within a small area. And this is one of the educational values of doing this kind of monitoring. We can also look at photo observations. For example, here's a photo observation of a grazing exclusion cage. And again, you can see a better view of that there. This is in northeast Oregon. That cage has been up for a couple of years, and animals haven't been able to graze within it, so we can see the differences there. So with Soil Health app, we can search by text, data type, user, or location. It's easy to import external data, and each project can have its own coordinators, data forms, and context maps, because no two places, people, or farms are the same, and they're not asking the same questions necessarily. So there's a lot of flexibility and adaptability with this. It's designed to enable shared intelligence and participatory learning, a flexible data design which allows better questions, for example, about function, about results, not just best management practices. It enables more people to ask and answer good questions, and it enables feedback to management, based on evidence and even quantitative evidence. It enables the contribution of creativity in terms of asking the questions and answering them, and where to ask those questions, as well as taking responsibility. What this is not is a research-centric data system or a closed silo where data is locked in and can't get out. Because we're dealing in these cases with complexity, not just simplicity, complexity, where the structure on the left is very risky because conflict is guaranteed, and while you may accumulate knowledge, there is little accountability for results. Whereas if we can grow a participatory shared intelligence, we can have the opportunity to become assets to each other and use the assets in our communities, the creativity, and take responsibility and get feedback based on evidence. And I think the opportunities for learning are much greater. When a problem can't be solved, we need to enlarge it. This is a key insight of complexity, that we can't stick to our siloed, narrow problems. We have to understand the web of causation that usually involves the largest planetary forces, such as carbon and water cycling, and how we manage those. If we don't share, if we don't engage in this kind of shared intelligence, we're locked into our own limited knowledge. And it's not just what you know, it's who you know it with. That's the whole idea of a shared intelligence participatory learning. So why are we doing this? Because we want to enable a local evidence-based shared intelligence and learning around ecosystem function, soil health, and watershed function. Better questions with more people participating. And we do seek partnerships and further development. So please contact me if you're interested or want to give us suggestions. or any good questions. Thanks very much.